Ready? Hello, everybody. Thanks for coming to the late session. Great turnout for right before the party. I'm Russ. I'm our VP of Data Platform, which means, I said it earlier today for those that went to the keynote, all the data that flows through TrueCar to service our applications, our business intelligence, our partners, et cetera, flows through this platform. I'm very lucky because I get to do a lot of the talking and present shiny slides, and people like Anil actually do all the work. So it's great that he's joined me up here. And what I hope in this talk, we tried very hard to deliver actual technical content to you. And I'm saying that you can only do so much of showing things in Hadoop through PowerPoint slides. It's like a totally terrible compression that happens. So what I want to do, and it'd probably be a little bit of a different framework, but I don't want to wait till the end and say we do Q&A and then we have time for one question. If at any point you want to know something, tell us. And we'll just take questions and we'll be fluid about it. And Anil right now is hating me for saying that because I didn't tell him I was going to do that. But the reason is that we'll present a certain story here of what we built in this image processor, but there's probably lots of little technical details that are relevant. And then certainly, where are we going with this? Why are we doing what we're doing with this? Which I can probably start there. Where's my, go forward. Sorry. It'll go. Can you flip it for me to the next slide?
Do we need to turn it on?
You figure that out. I'll keep talking. So we've been processing images for 10 years at TrueCar. Obviously, as the company's growth has accelerated, and the number of dealers and the number of vehicles that we're dealing with has increased. Obviously, so the number of images. 10 years ago when we started this and we wrote our original image processing, our requirements were super simple. If we have a vehicle image, just go download it and make sure it can be presented wherever it needs to be presented. There wasn't a lot of science to it. We need to scale this up, just for the total amount of data. Oh, good. You're going to be the operator, unlike what we said.
Sure.
So, we needed to scale this up very rapidly as the company grew. And our original processor was a single-threaded Java application that had almost no intelligence in it. And it would literally, you'd feed it a URL, it would go grab it, and then it would maybe thumbnail it and go put it somewhere. When I came to TrueCar 4 years ago, this is one of the key things I keyed in on, because I said images are one of the secret sources of really important data in our company. And as the world moves more mobile and more real-time with something like automotive, it turns out this is probably the most critical data that we actually have access to. And so what I wanted to do and set Anil, when he joined the company, out on was building us the world's largest automotive vehicle database we possibly could. I've referred to it in the keynote, and then I think some other people did earlier. The only way you can do machine learning is if you have huge data sets to train on. And so we really do need to get as many vehicle images as we possibly can. Challenge in automotive is that the sources of these vehicle images don't exactly lend themselves to a massively parallel operation of going and getting them. We have taken down several services and small CDNs by going and grabbing these images as fast as possible. That presents a unique challenge that Anil will get into in the technology. The other thing is, when we set out to do this, a lot of people are like, Russ, why do you want to put this in Hadoop? And hopefully this room gets it more than most. The idea was I was like, at the very least, we can send thousands of mappers out and just go get all the images, very straightforward kind of way. So of course, a developer before Anil went and did that, and then that's when we took down a bunch of services. I was like, you got to bound this a little bit so we don't blow everything up. But what's more important than just the downloading is that once you get it into a storage place where I can serve, 2 end consumers out of there, plus do the analysis, that's really powerful, because you can imagine that the 710 million images and what that will grow to over the next couple of years will far exceed, any other storage mechanism we had to do, actual analysis and actual just raw processing. So for me, it was just a natural, on the basic, go acquire these images, but then do interesting things with these images. I couldn't conceive of a better system to do this. When we started this, though, 2 years ago playing around with it, there were components of Hadoop and specifically HBase that weren't as mature as they are now. So now that there's some maturity in what we're doing there, we've actually, I think, Anil has put together a very beautiful system. And with that, I will turn it over to Anil, and then we'll interrupt as necessary.
Yep. Thanks for an awesome introduction, Russ. So first of all, then, what is image processing pipeline for TrueCar? So basically, image processing pipeline is used to acquire images of vehicles. It's used to identify updates or deletes to images. We also generate the unique URL of images for our websites, and we do crop and resize of images, copy our images to asset servers. Asset servers are nothing but an array of servers that are sitting at the front end and serving out images, and we also do deduping of images within vehicles. So this is one of the typical example of image processing pipeline. On the left hand side, you will see an image, but the URL over there is a URL that is coming from a dealer feed. We actually don't get the image file in the dealer feed, we only get the image URL. On the left hand side, once Hadoop image processor finishes processing this image, eventually it looks like that on our website. And
so let me, because I'll point out some things that may not be obvious. Here, this is a very fortunate example of where, for some reason, whatever the technology provider that the dealer is using in this case, just so happens they're hosting on Amazon, so we don't have a lot of performance problems and things like that. This also happens to be a very beautiful image that lacks a lot of gunky, salesy text and phone numbers and call me now and, hey, dude, look at this car. Like, that is something that in the processing we look for. We actually look for the presence of stuff we don't want the consumer to see because it ruins the experience. That's a little bit of complexity that isn't shown in this experience. But yep. you get the point of what we're doing.
So why we wanted to use Hadoop? Russ already gave some hints on it. So basically, we wanted to have high scalability for our image processing pipeline because this is one of the most important piece of our business. We also wanted to store historical data of images so that we can do analytics and machine learning on it. And since image processing pipeline is very important to our business, we wanted to have a fault tolerance in it. And then our legacy image processor also had another big problem. So the legacy image processor never used to check the original content of the image. It used to look for differentials in the image URL. So we have the image URL that we downloaded yesterday for a particular car, and today when we look for updates for the image, we will just check the string and make sure if the string matches with the image URL that we downloaded yesterday, we would consider that we have the latest image. But originally what dealers do, they don't update the image URL, but they will update the original image on their web server.
The short of that one is, if there's a bad way to do something, dealer technology will have implemented it that way. So
yeah, that was So what are the big data components that we used in Hadoop image processing pipeline? HBase. So HBase is used as a data store for archiving images and storing our current image data set. MapReduce. MapReduce is the computation engine for image processor. Kafka. Kafka is a public subscriber for pushing images to asset servers. OpenCV Java. It's the image processing library used for this project. Avro. At TrueCar, we have been using Avro to serialize our data on HDFS. So Avro for that.
But let me point out the Kafka part. It's very important that everywhere that we can, we protect ourselves and gives ourselves a way to throttle things. So Kafka and those kind of things allow us not to pound our own asset servers into the ground. So we do that all over our Hadoop infrastructure. Just make sure you have levers to pull to make sure that nothing can take anything else offline, especially anything that's going to be talking to something legacy in our technology.
So let's start talking about those components and their design within this pipeline. So let's take HBase data model. So for HBase, what we did, we created two tables for the image processing pipeline. The first table is called image, and it stores the current set of images with some metadata. And the second table is called image archive, Image archive is storing the historical data of vehicles as well as the images. The reason we created two separate tables for the pipeline is because we envisioned image table as a table which should be used for OLTP kind of workload, and the image archive table should be used for OLAP kind of workload. I will go into detail just in further slides. So, digging into the data model of image table. So, the row key of image table is VIN number. Basically, as per our business use case, we just do lookups on the basis of VIN number of the vehicle. So, the image table has two column families. The first column family is called I. So, basically, you might be wondering why did I call it I? It doesn't make any sense. The thing is that HBase is a key value store. In a key value store, the column name is stored with each and every cell. So, if we are making long column names, it's going to take more disk space, and when you do read and writes, it's going to do more disk I/O, and disk I/O is expensive. So, we try to save on that. It's a very generic pattern in HBase. So, the I column family is basically storing images. One column stores one image. And as this table was meant to be used for OLTP workload, number of versions stored over here is 1. Then the second column family is H. So, H is the column family which is storing basically the hash of the image file and some metadata regarding the HTTP headers that we have been fetching to track the updates.
But the real reason Anil named things like this was so that I could ask him every time, what does this column family name mean again? Which tends to be the model in Hadoop. Reduce semantic content to make it fast.
So, using multiple column families in HBase is not really popular, but we had a specific reason over here to have multiple column families. The reason is that the read patterns of column family I and H are mutually exclusive. So, basically, whenever I am trying to read the metadata, I do not need the images to be read from the disk just to get the metadata, and in one row I am storing all the images of a vehicle. So, it is possible that I might be storing like 100 images of a vehicle in one row, and then I also have metadata.
Well, it's actually great because I want to make sure people understand this. I have found vehicles where for some reason a dealer has uploaded 3,000 photos. So it's like we don't, part of the infrastructure we're trying to put in place is make no assumption about the scale of craziness that might exist in a data set. Just make sure it's not going to break if there's 3,000 images of a vehicle. Accept all the data and make sure people use it on the output however they want.
Yep. So basically here that's why we use multiple column families so that we don't do extra reads for imaging like metadata. Moving on to the image archive table, this is the table which is really meant to do analytics on our data set of vehicles along with their images. So again, the column family I is storing all the images, and column family A is basically storing the Avro objects that are flowing through the pipeline. We don't store the Avro object in a string format. What we do, we are using Java reflection to convert each and every fields of the Avro object into an individual column into HBase, and then the number of versions that we store in this table is 10 because we want to track the historical changes that the vehicle and the image is going through. The row key of this table is a composite. The reason we built the row key of this table is as a composite of provider ID, dealer ID, and vehicle VIN, so that if we want to do analytics over a certain provider ID, then we can just use the range scan of HBase and we can do the analytics for one provider. If we want to drill down onto a specific dealer, then we can also do that by providing the provider ID and dealer ID, and we can drill down on that one particular dealer.
So the kind of analytics that we do on that, you'd be surprised the kind of things that actually affect whether people buy a car. the number of images that they can actually view and kind of get a sense of the car, the quality of those images. Am I getting a full sense of the car? Are those images actually representative of the actual car? Because sometimes they can get mixed up, or for some reason people are marketing with an image differently than they are with the actual vehicle data. And then what he's talking about with provider IDs, there's different providers of data that give us stuff, and you also want to be able to measure the quality of that provider in terms of conversion and other things like that. And then there's all the other stuff we don't know about. Part of the thing that we do at TrueCar a lot is there's no end to the amount of spelunking we'll do to find improvements in the customer experience. So I gave Anil the directive that like you must store the data in as robust a way as possible, because I don't know what analytics I'm going to want to do in the future. I have some, but make sure that nothing is going to limit me in doing any kind of analytics going forward.
So these are some of the HBase tunings that we did. So when we start loading data in HBase, at the very beginning, we should pre-split the tables, because by default, HBase will create one region, and if we have a heavy load on the table, that's not good. That's not a good start. So if you pre-split the table, then you will get a better load balancing right from the beginning. As I previously said, HBase is a key value store, so if you can keep your column name short, it might help you in some performance. By default, HBase is good at managing around 200 to 300 regions within a region server. So in order to get to that ballpark, the recommended size of the region is around 8 to 10 GB, so we are using that. If possible, to optimize the writes on the client side, we can do client-side buffering, where we say auto flush is equal to false. What it does when you start submitting puts on the HBase client side, it will start doing client-side buffering, and it will not do a RPC call across the network. But there's one disadvantage, that if there is a failure in your application while you are writing the data, and if you are buffering, if the application fails, you might lose those writes. So you should make sure that you should be able to recover from those failure by replaying that data set or that process, and you should get to the state that you want to.
And to put it in business terms on that point, as a manager of a team, we call that client-side buffer a project manager. For when the developer fails to deliver the feature, they replay the conversation. Come on.
And we also disabled periodic measure compaction, because if the periodic measure compaction by accident it starts at the peak time of your job, you might have trouble running your job. By disabling periodic measure compaction, it's not like HBase will stop doing measure compactions. It will do measure compactions on the basis of number of store files that you have in your region. So now let's talk about the data overflow of the pipeline. So the input to image processor is the output of inventory processing pipeline. So inventory processing pipeline is another important pipeline at TrueCar, which is doing the processing of the vehicle listings data that is provided by our providers and dealers. And that vehicle listing data also contains the image URLs. So the input to mapper of image processor is the Avro objects of vehicle. We parse and validate those input objects as per the image processor validation, and then in the reducer we identify the CRUD operation that we need to perform on the image, and then as a consequence of that we do operations in HBase, and then we also do operations in Kafka, and then the asset servers are running Kafka consumers, so they are listening to the topics, and then they are pulling out images from Kafka. So,
yep, question. Go.
Do you have somewhere reading the image and trying to understand what exactly in the image, or it's just the metadata conversion already?
For the bulk, for the pipeline he's presenting, the view of it here is we want to, as quickly as possible, and this is a design pattern at TrueCar period, is get the raw data somewhere inside TrueCar into the cluster, like get it there, because there's just use cases where no analysis is needed, just go. and then have separate streams of that go where they need to do for analysis, because then you can retroactively go update, the content wherever you need to, which is just a pattern for us that works, because I think if you do too much of the upfront, trying to service every use case, you end up actually basically in the old traditional world of like do advanced ETLs that are super complicated, and then over time they don't scale well. Instead, we're just like, get it in there and then do operations as you need to on it.
In TrueCar, you do image processing or?
Actually analyze the image? Yes, absolutely. And I'll give you, as we go, I'll give you a couple specific examples. So we do some in real time and do some in batch on the back end.
So let's talk about how do I identify the CRUD operation that I need to perform on an image. So this is the reducer side. It's like the CRUD engine. So the inventory processor, as it moves along, it marks all the vehicle listing with their status. The status can be a delete, it can be insert, or it can be some other status. In the reducer, we first check whether the vehicle is marked as delete. If it's marked as delete, we just delete the data of that image, or we delete the data of that vehicle. And so here I would like to point out, we don't delete the data of that vehicle from the archive table. We just delete the data of that vehicle from the image table. And then we check whether if it's an insert. If it's an insert, that it means we never saw the images of this vehicle. So we'll just go ahead and download the images and then write them to HBase and Kafka. If it's not even an insert, then it probably means this vehicle has been in our system for a while. So now what we do, we fetch the HTTP request headers from the image URL that was provided in the feed, and then we also fetch the current HTTP request headers that are stored in HBase, and then we do a comparison of it. If the headers match, then we assume like we already have the latest image, and then we move on. If there is a header
pause
match,
because to your question, we had toyed around with more actual like image data processing in there, but it just gunked up the whole works. So literally inspect the content of it, and for what we wanted to do in a lot of cases, it was like, no, we're trying to find the minimum amount of information we have to inspect to make sure this thing is high speed. And then that's where you would want to, if you have something fancy you want to do it on the back end.
So,
because we found, he did a bunch of investigative work to actually read the content of the images, and then you run into the problem where, again, the download speeds, if you're waiting around for that download and to do the compare, it breaks it down.
So just to add on to what Russ said, so downloading an image file is actually 40% slower than just looking at the header, and it also gives an overhead on network, and it's also giving an overhead on our dealer and provider website. And just to give in perspective, these websites of dealers and provider, they are not very robust.
That was nice.
So now another thing that we did in order to speed up the image processor is getting like a cascading downloads effect within our MapReduce job. So basically we have that image processor mapper, and then the reducer of the MapReduce job is not a simple reducer, it's a chain reducer. So what it does in chain reducer, what you can do, you can create a DAG, and you can say map reduce and then map. You can chain multiple mappers after reducers, and what it does, it runs those mapper in a threaded pool, just like executor service within the same JVM of chain reducer. This is a really cool thing which got us a lot of optimization. So basically, so we start with chain reducer. In the image processor reducer, we start with a timeout of 500 milliseconds. So around 10% of image URLs are really slow to respond. They can take anywhere from 2 to 5 seconds just to respond. So you can imagine like how slow this pipeline is, just because we have a lot of latency from the image URLs. So in the image processor reducer, we try to set the timeout of 500 milliseconds. If we are able to, sorry, there's a mistake over here. Image socket, no, this is right, okay.
You know what happened in his engineering break? We reoriented the slide to landscape view.
Yeah, so if we get a timeout, then we go to image processor retry mapper. There, all we do is increase the timeout to 5 seconds. And if we are able to download that image in 5 seconds, we will just write it to HBase and Kafka. If we are unable to download it, we just say, hey, we just cannot process this image URL and move on.
Do you guys ever blacklist URLs?
Yes, we do. We have whitelist and blacklist for a variety of reasons, right? Because if you find a malicious URL, which we can inspect content for that, you want to blacklist it so that nothing even attempts to do it.
Is that looked up part of the pipeline or not?
There's actually, how do I want to describe this? We have it at the proxy level.
Yeah, we have a squid proxy, so we have some settings over there.
Which can also bite us sometimes, because if we don't update the list, and we're trying to be smarter even about updating those,
Yeah,
like have
recently,
machine learning that's like, okay, is he okay now? Like turn it back on so that Anil doesn't have to remember to have prod-eng fix squid. So.
A question?
So why are you trying to map for
So basically, I created 2 swim lanes. So the first swim lane is its velocity is 10x faster than the other one. So there I am saying, hey, you need to respond within 500 milliseconds to move from that process. If you can't, I have a slower swim lane because the volume of that data set is small. So if you imagine, if one image URL, it's taking 5 seconds to respond, I can process 10 image URL in that faster swim lane in that same period of time. So that's the advantage I get.
And it's a really good point. It's probably subtle, but again, at TrueCar, there is different value to different data. If you've got a slow provider of data or slow provider of a dealer or whatever, chances are it's an indicative of potentially slower business for them or something like that. So we tend to try and have the system prefer, the larger, more valuable sets of data, get those in as fast as possible without having to hand set all these things all the time.
Yeah, the another beauty over here, like, it would be really easy. I can add another one where I say the timeout is 10 seconds because it's already working out there. It's like a cascading effect, and I can keep on increasing the timeout if I want. That's the real feature that I would like to stress upon over here. So now let's talk about Kafka. So the image processor MapReduce job is acting as a Kafka producer. So we write one message per image file. The message format of Kafka that we are using is the key is the image file name. This image file name is also unique across the board for a given image that we download. That's also the feature that is built in the image processing pipeline. And the value is the image file itself. And the serializers that we are using, for key we are using the string encoder. For the value we are using default encoder. Default encoder is nothing but a byte array. It takes a byte array.
And he added this because I told him this doesn't have enough pictures in it to be compelling, so he put a picture in this one. So.
Thanks, Russ.
You got it. And now on this slide he's added humor as well, so this is good.
So we did some tuning on Kafka end also. So request required X, basically it means whether you want acknowledgement from Kafka brokers that your message was written successfully or not. By default it's 0, which means you wouldn't get an acknowledgement, which means your client will turn into an asynchronous client, but I wanted my client to be synchronous so that I know that my data is really getting written over there and then it's moving along. And then the other property is message send max retries. Basically it means how many times you want to retry a write to Kafka. The other one is retry back off milliseconds. Basically it tells how many milliseconds you should wait before doing another retry. The client ID is nothing but a string which you can say it's like an identifier which can be used for debugging purpose on the broker side. By default, is blank, which doesn't serve any purpose. So it's better if you put your application name over there. There's one real big thing that I would like to point out. So by default, the value of message send max retries is 3, and the value of retry back of millisecond is 100. So what that basically means, the multiplication of these two properties gives the real value, like how much time your Kafka client will wait for a failure recovery in Kafka, and it turns out to be 300 millisecond. And I'm still trying to find a big data application that recovers in 300 millisecond. So then we had failures because of that for like 1 or 2 days, and then finally when I looked at it, I changed the property, and then the system started performing better, because right now our Kafka cluster is not huge, but since we are pushing images at a very high throughput, it's like 1,000 images per second. So it was having some problem initially. So that really elevated the problem in our environment. So make sure you set these two properties properly to recover from Kafka failures. We also did some tuning on the Kafka broker side. Log retention bytes, by default it's set to unlimited, which should not be true. So we set it to 224 gig as per our environment. We also ran into problems on the Kafka broker side, because we were writing like 1,000 images per second. So we were getting connection refused on our client side basically. So the buffer size, the kernel buffer size on our broker machines or the broker settings were small as per our workload. So when we increased the buffer bytes, it started performing better, and we stopped getting connection refused errors. There are a couple of points that I would like to highlight. Data is purged in Kafka when any of like log retention bytes or log retention hour exceeds, it will start purging that data. And usually you should set your log retention bytes to disk space upon number of partitions on each node, just to make sure that you don't run out of disk space.
So question for Hortonworks. HTTP 2.3 Smart Sense is going to give us more realistic defaults, right? Yes.
Just since this is an image processing talk, I have to take up OpenCV also. So basically we used the Java bindings of OpenCV. We used Java bindings just to avoid using Hadoop steaming, because we wanted to leverage the native APIs of Hadoop platform. Java API, we have found it's pretty simple to encode, decode, crop, and resize. There is one caveat for all the Java programmers using these bindings. There is like a potential memory leak, even if you write your code in.
No Java programmer ever ran into a memory leak.
Yep, there you go. So basically, what's going on? So basically, if you are using like some native Java objects, their memory is recovered whenever they go out of their loop or something. But here, when the object was getting destroyed, but the memory was not getting recovered. So I would get out of memory error in my MapReduce job. And then I was just digging on internet just for the OpenCV Java bindings. And then I figured out that there is this documentation on this function which says release the memory or free up the memory. The problem is that they don't implement like closable or something. So at the compilation time of your application, you wouldn't get any warnings like you are leaking resources or something like that. So it's like you go and figure it out. So
pause there, because I want to go back to your question about processing. We explored in smaller pipelines the same kind of architecture, but OpenCV was doing much more. So for this particular application, he's talking about just getting the images in. We do very simplistic things with it, but obviously you can expose the full power of OpenCV.
No, it's only used in reduce phase. Map phase is just parsing and validation of the vehicle listing.
But you could. You could.
We could. So now let's talk about performance.
This is, Taylor, this is the slide.
So basically, you can see like the Hadoop image processor is scaling linearly, and our legacy image processor used to scale non-linearly.
This is why every day I was like, Anil, we have to launch this because this is not a made-up chart.
Yeah.
Things were getting very bad with our original technology, and this to me really is a money slide.
Actually,
it's like,
this is a positive chart for our legacy pipeline.
well, in some way,
It is.
it depends. I could flip it. I mean, but you're talking astronomical. Like you're not going to keep up. You know, you saw earlier our business is growing so fast. So this problem is only going to go off the charts.
So yeah, just to give so in last 5 months, the volume of images that we need to process every day has grown by 90%. So we are growing like really fast on the volume of images, and we were unable to keep up with that. So now, as I said, we did that cascading download stuff. It gave us a performance improvement of 20%.
Which is, again, when you're looking at scales of hours and days, if you hope to do anything with machine learning on images, you have got to eke out these gains. I just fundamentally believe it. That's why I pulled back. I keep talking to you about it because I pulled this back from getting too fancy with the downstream science of like analysis. We certainly did a lot of that, but I was like, until we've got this thing fully tuned on the full set of images, like don't go down that way, because what will happen is the scientists will spend all their time optimizing the one little function, and it's the upstream thing that will slow it down. So,
And this is
my slide.
Yep.
But this is where you don't leave a developer with an incomplete spec. I told him I need a brain in every deck we do, and he came back with this cartoon. So, but there's a serious point, and I wanted to get at it, and I wish we had more time, but it needs to be a separate talk of some of the more inventive things that we do with all this image data. I encourage you, and it'll be a lightweight thing, but you can experience some of what TrueCar does with image processing. If you get the app, and if you go to a TrueCar dealer, a certified dealer lot, and it will tell you in the app if you're near one or on one, and you can do a feature called price check, which will let you walk up to a car and scan the VIN, just scan the VIN code on the window sticker or on the actual, some of them have VIN barcodes. And we'll do a bunch of OCR on that to detect that car and then give you back a price. We went further on that, and I'll tell you, we did this, but we pulled back from it because the user experience is really funky. On the window sticker is probably the biggest, everybody knows what a window sticker is. It's probably the source of truth for what's actually on a vehicle, like end to end and all the fees and everything. And so one thing we set out to do, and this was before Neil got here, and I'd hired a guy out of JPL and all these places, and he was a guy searching for black holes, and I'm like, I got a more interesting problem. Figure out how you can get window sticker, like detect all the data on a window sticker and extract it in real time. And he actually got pretty far. The team got pretty far with this. Just if you had a perfect, window sticker without all the real world stuff, we got pretty far with being able to take that image, OCR it, recognize which data objects we actually cared about, and all off-the-shelf stuff that we were just tuning, different things in OpenCV and with different OCR libraries. The problem got when you actually went to a dealer lot, different times of the day, depending on how clean the window was, you get all sorts of weird artifacts that make it very hard to then run those off-the-shelf algorithms. So I pulled us back from advancing that science because, to an end user, and this is where all these things add up to me thinking about the overall business, which is if it becomes too hard for a user to perfectly line up their phone to do something cool, you've lost the whole point. So it's just a practical example of like, you can do science too much and then you got to make a choice. I see a question, go for it. Crowdsourcing in the acquisition of data or in the images? Yes, but convincing people to go to dealer lots and take pictures of Well, this would be an interesting, and we have talked about exposing the actual data to the outside world so that they can just take the raw images and do all sorts of interesting analysis on them. Absolutely would be an interesting project to throw out there, but we haven't done it yet, so.
We're done.
Yeah, we're
So,
done. And
thanks, everyone.
If there's any other questions, we're happy to
Yep.
answer them for you one-on-one or however you want to do it. So thank you all very much. Very much
Thanks.
appreciated.